Okay, so part two, I want to talk about why does the Diffie-Hellman key exchange work. So this will be a very similar lecture to my walkthrough of the Diffie-Hellman key exchange using exponents mod a prime. So from the point of view of an algebraist, we're doing the same exact thing, right? We've got two different people. We're going to pick a generator. We're going to add that generator to itself a number of times, and then see what we get. The only difference between when we did this a couple months ago and doing it with elliptic curves is that we have changed the group that we are working in. So, as is traditional for these kinds of demonstrations, I'll have two different people, and we'll call them Alice and Bob. And they want to establish a shared secret that, in theory, no one else, even someone who is snooping on their conversations, would be able to determine their secret. So Alice and Bob need to agree on certain parameters, and in our tutorial I just told you what parameters to use. Alice and Bob need a prime modulus, we'll call that lowercase p. They also need an elliptic curve, right? So some formula y squared equals x cubed plus ax plus b. And they'll need to make sure that it's not singular or self-intersecting, right? So we can check the discriminant and all that. And finally, Alice and Bob need to agree on a generator, which I'll call capital G, right? So this is an element of the elliptic curve group, which means it's a point, right? G is some x and y coordinate pair that satisfies this equation, right? It is a point on the curve. At this step, everything that Alice and Bob have agreed to is public information. It doesn't actually matter if an attacker knows this information or not. So they might as well be posting this on Facebook or something. In terms of the secrecy, Alice and Bob both need to pick their own secret multiplier. And I see a little bit of a collision in notation. Alice and Bob are going to have their own integers, A for Alice, B for Bob. And as I am reading this out loud, I want to make clear that these are different from the A and the B that's in my formula up here. So I'll probably change this up for when I post these slides online. But the important thing here is that Alice is not going to actually tell anyone what her multiplier A is. And Bob is not going to actually tell anyone what his multiplier B is. Instead, Alice is going to calculate the point A times G, right? So G is some point on the elliptic curve. Alice calculates what you get from taking A copies of this point and adding them all together. And that is something that, she won't be doing this by hand. In practice, A will be some very large integer. So you can just have a computer make this calculation, and that'll be a fairly quick calculation at that. Bob is going to do the same thing. Bob calculates the coordinates for his multiplier, B times G. So this is B copies of the point G all added together. And so instead of disclosing their secret multipliers, Alice and Bob are going to publish the x and y coordinates of their new points. Alice publishes the xy coordinates for A times G. Bob publishes the coordinates for B times G. The reason why this is secure, in theory, is that An attacker needs to know one of these secrets in order to solve for Alice and Bob's shared information. But that would mean solving the discrete logarithm problem for the elliptic curve group, right? If you know the point G that Alice started at, and you know the point A times G that Alice finished at, but you don't actually know what number A is, there is not a fast algorithm to recover what A is, right? You can imagine someone trying just a brute force. Let's calculate 2 times G. Let's calculate 3 times G. Let's calculate 4 times G. That is not a very efficient attack here. So Alice and Bob each have their secrets. They've each published information that does not reveal their secret. And then what was the final step of the tutorial? You take the other person's point and you calculate your multiplier times their point. So Alice takes Bob's coordinates for B times G. She knows the multiplier A because she picked it. And so Alice calculates A times the point B times G. So this is A copies of the coordinates that Bob published, all added together inside the elliptic curve group. On the other hand, Bob is going to take Alice's coordinates for A times G. Bob does not know A, but he knows the multiplier B because that's Bob's secret multiplier. Bob calculates B copies of Alice's coordinates and adds them all together, right? So A times G here in parentheses, this is standing for the X and Y coordinates that Alice published. Bob doesn't know what multiplier is here. So that's what it looks like from Alice's point of view and from Bob's point of view. But from the algebra perspective, all we're really doing is we're starting at the point G, and we're going to calculate what we get from combining A times B copies of the point G, right? So A times B will be my multiplier. That is how many copies of the point G we put together. Bob can calculate that from his formula here, using information that he knows. Alice can calculate it using her formula here, using information that she knows. They both get the same answer because A times B times G and B times A times G end up being the same thing in this group. So now both Alice and Bob have the same finishing X and Y coordinates. And if you're on the outside, you would know the coordinates for Alice's point, A times G, and you might know the coordinates for Bob's point, B times G, but you can't actually find the coordinates for A times B times G unless you know one of the secret multipliers. So at this stage, right, we have finished the key exchange. Alice and Bob now have X and Y coordinates that, in theory, no other person should be able to calculate. Now, it's one thing to agree on a secret number that's a little bit short of actually sending a message, right, something more meaningful. But you can use these secret coordinates for setting up another crypto system, something that you'd actually be able to send a message down. So one thing you could do is you could use the X coordinate maybe as the seed for a random number generator, and then both Alice and Bob would have the same random bit stream because they start their random number generator in the same place, and they could talk to each other using, say, one-time pads. They could also do something like that to decide on another crypto system to use. Maybe they could pick a different prime number, or maybe they could establish, maybe not RSA, because we just talked about how RSA is starting to age out a bit. But they have lots of options open to them for what to do next. The point of this lecture is just what algebra makes the exchange work. How can we guarantee that we have the same answer whether we are Alice or we are Bob? Okay, that is it. I will see you early next week. Have a nice weekend.